Unit 6, Topics 1 and 2, Basic Probability, Compound Events, and Complement Rule. Probability is a measure that is associated with how certain we are of outcomes of a particular experiment or activity. An experiment is a planned operation carried out under controlled conditions. If the result is not predetermined, then the experiment is said to be a chance experiment. Flipping one fair coin twice is an example of an experiment. A result of an experiment is called an outcome. The sample space of an experiment is the set of all possible outcomes. Three ways to represent sample space are to list the possible outcomes as a set, to create a tree diagram, or to create a Venn diagram. The upper letter S is used to denote the sample space. For example, if you flip one fair coin, S is equal to H and T, where H equals heads and T equals tails are the outcomes. Now, one thing to think about in this case is if we were looking at, say, flipping a coin twice, our set would be something more like HH, HT, TH, or TT. See now that those are all the possible outcomes. An event is any combination of outcomes. Uppercase letters like A and B represent events. For example, if the experiment is to flip one fair coin, event A might be getting at most one head. So that's a different one where we're talking about like what's the probability of getting at the most one head or at least one head. The probability of an event A is written P of A or probability of A. Probabilities are between 0 and 1 inclusive. That is 0 and 1 and all the numbers between the values. The way to think about this is that if something has a 0% likelihood of happening, its probability is 0. If something's 100% of happening, that probability is 1. So we have here probability of A equals 0 means that the event can never happen, and probability of A equals 1 means that the event always happens. So for example, if you want to know if I flip a coin, if the probability is going to be heads or tails on one flip, the probability is going to be 1 because it has to land on heads or tails. When we say things that are equally likely, it means that each outcome of an experiment occurs with equal probability. For example, if you toss a fair six-sided die, each face 1, 2, 3, 4, 5, or 6 is as likely to occur as any other face. If you toss a fair coin, a heads or and a tail are equally likely to occur. If you randomly guess the answer to a true-false question on exam, you are equally likely to select a correct answer or an incorrect answer. Probabilities will be expressed as decimals or fractions in lowest terms. I will say, just on a side note, just in the real world of statistics, we typically look at probabilities in decimals, not in fractions. It does, especially in this level of math, we do still look at fractions, but you would typically see that as expressed as a decimal later down the road. How to calculate the probability? There are two methods, one theoretical method and two relative frequency method. One, to calculate the probability of an event when all outcomes in the sample space are equally likely using a theoretical method. Count the number of outcomes for event A and divide by the total number of outcomes in the sample space. So here we have probability equals number of outcomes divided by the total number of outcomes possible. Example number 1. So if you were to toss a fair dime and a fair nickel, the sample space is HH, TH, HT, and TT, just like we talked about right here, where T is tails and H is heads. The same sample space has 4 outcomes. A equals getting one head. So let's look at this right here. When we say getting one head, that refers to either this outcome or this outcome, which means that it's two possible outcomes satisfy that event, and there's 4 total outcomes. So that would equal 1/2 or 0.5. Example 2, at the fair, the duck game has 6 blue ducks, 7 green ducks, and 8 yellow ducks. And 3 pink ducks floating in a pond. What is the probability that Susie randomly selects a yellow duck? So here the total number we have is 6 plus 7 plus 8 plus 3 gives us 24. So that's right here on the bottom. That's the total number of ducks. And there's 8 yellow ducks. So the number of chances that she has to satisfy that event is 8. So it would be 8 out of 24 or 1/3 or 0.33 if we were putting it in decimals. 2, to calculate the probability of an event using the relative frequency method, count the number of times the event occurs and divide by the number of attempts to achieve event. This method is used when performing experiments. So number of times the event occurs divided by the total number of times the experiment is performed. For example, Bob went fishing. He cast his fishing line 40 times during the fishing trip, and of those times he caught a fish 8 times. What is the probability that Bob catches a fish on any one cast? So the number of times he caught a fish was 8. The number of times he cast was 40, so 8 over 40 or 1/5. Now, this one's actually kind of important, and we use this a lot in the world of statistical modeling. You're using historical data to help you decide what the likelihood of it happening again are. So while it's not exact, it definitely gives you a good idea based on your experience. So here we have some examples. So let's look at the first one. A baker finds several new recipes to try. Of the recipes, there are 12 cookies. I'm going to go ahead and write this down on my tablet. 12 cookies, 11 muffins, and 5 cakes. We want to know if the baker selects a recipe at random, what is the probability the recipe is for cakes? So the probability of getting a cake. Or give your answer as a fraction. So what's the probability of a cake? Well, here's our 5. So now we're looking at that first method that we talked about, right? Theoretical. So we have 5 over, and what's our total? We have 12 plus 11, that's 23, plus 5 more, that's 28. So we have 5 over 28, and that cannot be reduced any further. Since 5 is a prime number and 29, so that would be our answer, 5 over 28. All right, Ryan finished his daily jog and wants a drink. In his refrigerator, there are 4 cans of energy drink, 10 cans of soda, and 12 bottles of water. If Ryan chooses a drink at random, what is the probability that he chooses a bottle of water? Again, so we're going to say the probability, let's go and make this a little smaller. All right, so we're going to say the probability of water is going to equal the number of water bottles. So what do we have? 12 bottles of water divided by, what's the total here? We have 4 plus 10 plus 12. So that's 26. But that can be reduced, right? So let's go ahead and reduce that a little bit. Let's divide both by 2. We're going to get 6 over 13. So it's a little over half, right? All right. Numbers 3 and 4 are very similar to 1 and 2. So let's get down to number 5. Martin is a food critic reviewing a restaurant that has 7 main courses, 3 desserts, and 5 appetizers he has yet to try. Martin asks the server to surprise him with one of the remaining items. What is the probability that Martin is served a dessert course? So again, very similarly, we have a total of 7 plus 3 plus 5 that he has not tried. So that's 15, and he's saying we're asking what is the probability that Martin is served a dessert? Well, there are 3 desserts, so the probability of a dessert equals 3 over 15, which equals 1/5. And let's skip down to number 9. A deck of cards contains yellow cards numbered 1, 2, 3, 4, 5, 6, purple cards numbers 1, 2, 3, 4, 5, and blue cards numbers 1, 2, 3, 4. If a single card is picked at random, what is the probability that the card has an even number? Interesting. So we have a lot of numbers here. So we have 1, 2, 3, well, we have 6 plus 5 plus 4 total cards, right? So the total number of cards equals 6 plus 5 plus 4, which is 15. And we want to know what is the probability that the card has an even number. So let's look real quick. We have 1, 2, 3, 4, 5, 6, 7 possibilities of getting even. So the probability of getting even equal 7 over 15, and that can't be reduced anymore, so that would be our answer, 7 over 15. Next, we're going to talk about the basic probability of compound events. How to find the probability of a compound event. List all the outcomes, identify the outcomes in the compound event, These are the desired outcomes. The probability is the number of desired outcomes divided by the total number of outcomes. So we have an OR event. An event is an event. An outcome is an event. So here we have A or B. If the outcome is in A or B, or is in both A and B. So that means it applies to all of the possibilities here. For example, roll a six-sided die. Let A equal rolling an odd number. So you see here in A we have 1, 3, and 5. And let B equal rolling a number less than 3. So the less than 3 only leaves us with 1 and 2. So you have 1 here in their intersection and 2 over here in B. So the possibility of getting A or B equals 1, 2, 3, or 5. Notice the only one not there is 4 because it didn't fall into either of those sets. Notice we do not list one twice since it is in the overlap or intersection. You only list that number once. So the probability of A or B, so remember that's the division of number of desired outcomes divided by the total number of outcomes, and it asked what was the probability of getting A or B. There are 4 possible outcomes in A or B, so that's 4 over the total number of outcomes, which is 6, right? We have a 6-sided die, so when we reduce that we get 2/3. Next, we're going to talk about an AND event. That's the intersection. Remember we talked about that in the last unit. So an outcome is in the event A and B if the outcome is in both A and B at the same time. So here it's that shaded area in the middle, that intersection. For example, roll a 6-sided die. We're looking at the same type of example. Let A equal rolling an odd number. We're looking at the same thing. We have 1, 3, and 5. And then B is, again, rolling a number less than 3. So we just have 1 and 2. So 2 is in B, and 1 is the only thing in that intersection. So then down here, A and B equals 1 because 1 is the only outcome in both A and B. The number of outcomes in A and B is 1. So when we look at the probability of A and B, that's the intersection, it's going to be the number of desired outcomes 1 divided by the total number of outcomes 6. 1/6. So the probability of getting a 1 is 1/6. The complement of event A is denoted A prime or A complement, AC. A prime consists of all outcomes that are not in A. So here is your set A, and the complement of A is all other outcomes that are not in set A. Notice that A and A complement give the entire sample space S. Therefore, probability of A plus probability of A prime equals 1. For example, let S equal 1, 2, 3, 4, 5, or 6. So that's again, a 6-sided die kind of situation. Let A equal 1, 2, 3, 4. Then A prime equals the other number. So up here, if we take out 1, 2, 3, 4, all we have left is 5 and 6. So A prime or A complement equals 5 and 6. The probability of A is 4 over 6, right? We have 1, 2, 3, 4 over 6 possibilities. And the probability of A prime is 2 over 6, because we have 1, 2. Notice the probability of A plus the probability of A prime is 4, 6 plus 2, 6, which equals 6, 6, which just equals 1. So this is the complement rule. The probability of A equals 1 minus the probability of A prime, and the probability of A prime equals 1 minus the probability of A. The reason for this is because when we just said the probability of A plus the probability of A prime equals 1. So if we were to subtract probability of A prime from both sides, this cancels, so we have the probability of A equals 1 minus the probability of A prime. And the same applies for the A prime, right? So if we start again with probability of A plus the probability of A prime equals 1 and subtract probability of A from both sides, these cancel and we're left with probability of A prime equals 1 minus the probability of A. All right? So that's going to be the part 1. I'm going to pick up with some examples in part 2, and we'll go from there. So let me know if you have any questions about this much so far.